This solar inverter came to me completely dead, burnt inside, not even turning on. The customer already took it to the service center 3 times, and every single time it failed again. They finally gave up and handed it to me. At first look, it seemed like an impossible fix, but watch carefully, because by the end of this video, this inverter will go from dead to alive. It's the PV5200, a 4 kilowatt solar inverter. These 2 terminals are the input for connecting solar panels. Over here is where the mains input and output connect, and these terminals you see are for the battery. This side is positive and this side is negative. Let's open up the inverter and see what we find inside. We'll remove these connectors from here and set them aside for a while. We'll reconnect them later when needed. I've taken the PCB out of the box. As soon as I removed it, I noticed some burnt components. Look here, the MOSFETs are burnt, badly scorched in this area. Many of them are literally blown apart. This one is split open and so is that one. Pretty much all of them look burnt. You can see all the blackened spots here. If I flip it to the back side, the situation looks very bad as well. This entire DC section, which connects to the battery, is completely burnt. There were some transistors installed here. This one has melted down entirely. The customer also told us this is the 3rd time it has failed like this. Previously, they sent it to the service center for repair. It was fixed, worked for a day or 4, then failed again. They sent it back to the service center, it was repaired again, then failed again and was repaired once more. This is now the 4th time. For this 4th attempt, they've given it to me to repair because they don't want to send it back to the service center. The service center repair works for a few days, and then the unit completely bursts out like this again. I'll try to repair it now. I'm checking parts under the microscope to see if anything else looks burnt, cracked, or damaged, so we can replace it easily. Before doing further work on this PCB, we'll remove the control system or control circuit from here, because working with it attached to the board is a bit difficult. If it accidentally breaks or gets damaged, that would create another problem. You can see there's a screw here. And another screw is here. Let's remove it as well. This is the base and there are pins inside the base. See, I'm removing the base. The pins all come out. There are 2 connectors here. This one is the base connector, and this one is the male connector. This is the control board that holds the microcontroller and other components. I'll take it out from here. It's necessary to remove it. Now it's completely separate, and now we can work on the rest of the board more easily. Before proceeding further, we'll remove all the components that are already faulty. If we keep working with them in place, nothing will be repaired correctly, so we'll take them out. There's a sensor installed here. We'll remove that as well. Now we'll also take out the heatsink. For that, look, there's a screw here and another here. We'll remove them. The heatsink is now off. You can see all these burnt parts and this MOSFET is blown. Everything is clearly visible now. All of them are bad. This last MOSFET is also gone. That means none of these are likely to be safe. We'll remove them from here, cut them off and set them aside. After cleaning, we're checking that none of these pads points are bridged. When we do further testing, if any of these points are connected, it can show a short circuit. None of the points are shorted together. Now we'll proceed to more testing. On this side we have the IGBTs. We'll test them too because they were previously replaced. Let's check. This is the gate, and these are the collector and emitter. Let's check these pins. I'll set the multimeter to diode mode. It seems shorted to me. We'll swap the probes with each other. This one is reading 0. See, the gate and collector are shorted together. Let's check the next one. This also shows 0 voltage drop. It seems all these IGBTs are shorted here, likely because work was done on this before. This one is also showing 0 voltage drop. Next, gate to emitter shows 0.5 V, so this IGBT looks somewhat okay. But we won't risk using it. Often an IGBT appears fine in circuit, but once you remove it, it shows short, or it may be weak. As you can see, this one is also indicating 0 voltage drops. It's increasing a bit, yes, but this point is also degraded. Look, this one also shows 0 voltage drop between the gate and drain pins. The next IGBT is also showing 0 volts. Let's check the other pins as well. These pins are shorted too, so almost all the IGBTs are shorted. We'll remove them too because testing the system with shorted parts is difficult. You see shorts everywhere. It's a bit difficult to remove them this way, so we'll use a proper removal technique. And someone has installed this particular number of IGBT here. I have removed about 9 IGBTs from here. There's also a diode installed here. Let me check that for you. Sometimes a bit of debris, like a tiny piece of solder, sticks between small pads and causes a short. That's why cleaning is extremely important, no matter the situation. For example, I still have more work to do on this board, but I will definitely give it a thorough cleaning first. Otherwise, later on, if I forget and continue working, it may cause a bigger issue. After cleaning, we'll test again. Here you can see the diodes, diode 38 and diode 35. We need to test these too. On diode mode, it shows a forward voltage drop of 1.90 V, which means this diode is fine and there's no fault. Next, we'll check the other one and reverse the polarity. Still fine, so this diode is okay too. Now we'll check the next one. We checked 35, now 38. Now I'll change the polarity of the probes. This one is fine too, no fault here either. The reading shouldn't be 0. If it shows 0, that diode is bad. Let's check again. This diode is showing 0, 0. If we test the diode directly, it shows 0, but if we test over here, it shows a voltage drop. The diode next to it also shows a voltage drop, whereas diode 35 is showing a short. So we need to check all the diodes installed here, at all 3 points like gate, collector, and emitter. That way we'll identify all the faulty diodes and replace them. We'll keep checking all of them. See, this one shows 0. If the voltage drop is 0, the diode is short. We'll replace this one too. This one is short as well. The next one shows 0 voltage drop too, and so does the next. Let's reverse polarity, same result. That means all these diodes here will be replaced. Along with them, these 47 ohm resistors, marked 470, should also be checked. See, all these resistors are installed here. And here, look, 4992, and if we check its value, it shows 48.5 kilo ohms, so I think it's a 50 kilo ohms resistor. We'll replace all these diodes here because they're all shorted. After removing the diode, it no longer shows a short circuit. The reason it appeared shorted in the system earlier is because it was connected in parallel with two 45 ohm resistors. Due to these resistors, the circuit was showing 0 voltage drop. This diode, along with the two resistors, is used to discharge the IGBTs gate. When the IGBT is switched on, the emitter and collector become connected, which completes the circuit. After that, the circuit needs to be disconnected again. If even a small amount of millivolts remains on the gate, the IGBT would stay turned on, which could potentially damage it. That's why these resistors are used. They discharge any residual millivolts present at the IGBT's gate. As a result, the continuity between the emitter and collector is eliminated. I initially installed an SMD-NPN transistor here by mistake. Upon double-checking, I realized that a PNP transistor should be installed in this position. That's why I am now installing a DIP PNP transistor with the number 9012. Since I don't have this IC in an SMD package, I'm using the DIP version instead. Before installing the IGBTs, it is very important to check their drive circuits. The procedure is that neither the DC MOSFETs nor the IGBTs should be installed at this stage. Now, we need to measure the voltages between the gate and emitter of all the IGBTs. Each IGBT's gate to emitter voltage must be exactly 4.7 volts. If for any reason the voltage on any one IGBT is either lower or higher than 4.7 volts, then we must also check the drive section for that IGBT, since that's where the problem would lie. If any one IGBT is not getting voltage, it can mean the microcontroller isn't receiving the necessary outputs or other information, so it won't re-enable the drive signals. The procedure, then, is to cut power to the system and power it back on from the same IGBT where the voltage was missing. If the voltage appears after reboot, then it's fine. If the voltage is still missing, there may be a problem in that IGBT's drive section. In our case, the voltages on all the drives are perfectly fine. Now we'll install all the IGBTs and work on this DC side, the output and the charging side, and see whether everything functions properly. Let's remove this. Now we need to discharge it. So any remaining voltage is bled off. It's discharged now, so I can work on it safely. Finally, I've installed all the components here. I showed you the IGBTs and everything I installed. I've properly reconnected all the connections. This model requires 24 volts, and I have a power supply here. I'll turn it on. On the second channel, I've set 24 volts, and I've connected the wires. Now I'll press the output button. I turned it on. There's no voltage or anything here yet. Now I'll switch on the inverter's power switch. I turned the switch on and it started giving a beep sound, and you can see 230 volts are now present here. We have 24.3 volts on the DC side and 230 volts on the output. So our battery setup is perfectly fine. No problems there. I expect the remaining functions will also work properly. Here you can see the sensor is unplugged, so one of the fans has stopped. We'll install these properly too. That's the only thing left. Almost everything else has been installed. The system just shut down. Now I'll obtain 310 volts DC from 220 AC volts and use that to feed the solar MPPT section. I've prepared everything. The connections are made and I have 220 AC volts available here. I'll apply 220 AC volts and you can see it on the multimeter. We are getting 305 DC volts and the system is running. The inverter is receiving 304 volts. I will switch on the power button of the inverter. The fans are running. The output will appear shortly. And now the system has provided the output. About 230 DC volts are now coming from the solar side. The solar system has started as well. It shows PV, and the battery is absent. You'll notice the voltage fluctuates a bit because I've built this supply myself. I'll show you that in another video. So we're generating about 310 DC volts from 210 AC volts. Right now it's around 269 AC volts. There's a slight drop, but no problem. It won't affect operation because the system is running smoothly. We're getting 270 volts from the solar side and 230 volts at the AC output. Perfectly fine. The last check will be the mains input. I've already connected the AC input here and the system is fully ready. Now I'll turn on the mains. I turned it on. The system powered up. Now the 230 volts are coming from the mains supply. I'll turn this switch on. See, the supply is 230 volts in and 230 volts out. The supply is ready now and notice the indicator color is blue. Everything is okay here as well. Our inverter is fully ready to be delivered to the customer.